Okay, so we are picking up with the second half of the lesson video from 6.5, taking a look at interpreting these accumulation functions, and specifically we're talking about accumulation functions where we're doing some graph analysis, okay, where we're looking for critical points and increasing, decreasing, all of those types of things. So this is where I said that I was going to just pause and let you copy this down. I'm actually hopeful that you can figure most of this out on your own. But I do want to point out that if we're talking about g of x that's defined as an integral, what that really means is that the derivative of g is just f. So if you're looking at f, you're really looking at the derivative of g. So all these questions that say occurs when f of t does something, you want to be thinking about, well, what would the derivative be doing? The derivative of the g function be doing in order to make the g function do all of these things. So all of these things should look familiar from when we've talked about this before. So I'm going to zoom this out just a little bit. If you needed to take a second to pause and copy these things into your notes, you're welcome to. I'm not going to talk through all of them because you've definitely seen this before. Okay, let's hit an example that's a little more complicated where this relationship is not quite so direct between g prime and f. Okay, so we see another graph here. Okay, the graph is f of x. You've got g of x defined here, but notice that g of x has some other stuff in it. So it's not just an integral anymore. It's got this x squared in front of it, and it also has an integral going up to 3x instead of just x. Okay, so I'm going to make that key off to the side. And we have our g of x function is an integral function. But we have to keep that x squared in mind, and we have to keep the 3x part in mind. So I'm just recapping the function right now, just so I have it for later. And then if I have to evaluate this part of it, we want to remember that that's really talking about an area, right? An integral is talking about an area. Let's suppose I get asked about g prime. Well, g prime is the derivative of this thing. So let's take our derivative step by step. First of all, the derivative of x squared is 2x. Now, when I do the derivative of this thing, first thing we'll do is take the derivative of the 3x. We'll have 3 times. And then remember that 3x drops down into here, so this would be f of 3x. Now, this f of 3x thing, I mean, we might have a little bit of algebra to do there, but it's important to recognize that that is just talking about the graph itself. Now let's define g double prime. I'm not sure if I will need to know g double prime down here. Probably good to do as an example here. Okay, g double prime would be the derivative of this thing. So 2x, derivative is just 2. Now, if I handed you this like 4 months ago and I said, tell me the derivative of that, I really, really hope chain rule would pop into your head. Because when I do the derivative of f of 3x, the first thing I need is the derivative of the 3x, which is a 3. And then 3 times this 3 gives me a 9. And then this would become f prime of that 3x. So this 3 became a 9 because I multiplied by the inside derivative using chain rule. And then because I took a derivative, my f became an f prime. F prime is going to be talking about a slope. It's kind of always these 3 things, right? Area, graph, slope. Okay, so when I say that I want g of 1, let's write out what this would look like using our g of x function. G of 1 means I need to do 1 squared plus an integral from 1 up to 3x, and my x is 1, so 3 times 1 is 3 of f of t. Pause and make sure that makes sense to you. This 1 became my x, so I put it in for that x and I put it in for this x, right? To evaluate this piece, I need an area. So I need my area from 1 to 3. That's this area here. I might regret scribbling all over that. But this would be, the 1 squared is just a 1. this is going to be a circle with a radius of 2. So it's going to be pi times 2 squared. But then that's like a quarter of the circle, so we're going to divide that by 4. Well, that's just a 4 divided by a 4, so this answer is just going to be a 1 plus pi, because the 2 squared and the 4 cancel each other out. That's my answer for g of 1. So this g of x function, like I could graph this thing separately. It doesn't look anything like this. Okay, this is the f of x function. But this would be the value of that g of x function at 1. Okay, let's try it again with g of negative 2/3. Okay, so that would be, and maybe pause now and see if you can get ahead of me here. Negative 2/3 squared plus an integral from 1. Now 3 times negative 2/3 is going to leave me with negative 2 f of t dt. Okay, so negative 2/3 squared is going to give me a 4 over 9. Whoops, let's write an equals there. Plus, okay, area from 1 back to negative 2. Well, I'm seeing a trapezoid here, right? This shape right here is a trapezoid. And here's the thing I need to look out for. This is a negative area because it's underground, but I'm also walking backwards. So technically this would be like a subtraction because I'm walking backwards of a negative number, and those are going to cancel each other out and turn me back to being positive because I'm walking backwards and being negative at the same time. My area of my trapezoid would be 1/2. The height of my trapezoid is up and down here, so this has a height of 4. And then my bases, this has a length of 3, and this has a length of 1. Okay, and so then as a final answer here, I'm going to have 4/9 plus, because of that double negative, this will really just be a 2 times a 4, so that's an 8. If I really wanted to clean this up some, I can make this, what's 8? 72 over 9 if I multiply by 9 there. So then my final answer here would be 76 over 9. Don't care if you simplify that or not. Don't care if you make it a decimal. Really, this is the important part, is understanding what is happening here. Okay, let's try g prime of 1. So we're going to use our g prime as a guide here. Okay, so if I'm doing g prime of 1, this says that because it was a prime, this is going to be 2x, so 2 times 1 plus 3 times f of 3x, and my x is 1, so that's just f of 3. So that's 2, whoops, not times, plus, I just did 2 times 1 there, 3 times f of 3, remember f is just the graph, so f of 3 is 2. This one's actually easier, right? Without having to do that area. That's 6 plus 2, so that's 8 as my answer there. That's g prime of 1. So if I were to graph this g of x function, which, again, I don't really have a way to do that because I don't have an equation for my f of x function, but that's fine. But if I were able to graph this, then at x equals 1, my tangent line would have a slope of 8. That's what this is telling me. Okay, so one more to hit here. Is g of x concave up or concave down at negative 1.5? To answer this question about concavity, what I need to know is g double prime, right? I need to know, is g double prime positive or negative? That's the question that I'm being asked. So it's a sneaky way to ask you another one of these, but like with purpose, right? So I need g double prime of negative 1.5, which if I'm using my key here, that would be 2 plus 9 times f prime of, so this is 3 times negative 1.5 I guess I could have written that out for you, but wanted you to see what I was doing there. So that's 2 plus 9 times f prime of negative 4.5. F prime is talking about a slope, right? So I need to look on my graph at negative 4.5 and decide what my slope is. So negative 4.5 is going to be, I don't know, somewhere in here. But really, as long as I knew the slope, I'm sorry, you can't see the whole graph. As long as I know the slope of this line somewhere, that should be my slope at negative 4.5, right? I can only ask you those slope questions if we're talking about straight lines. So my slope here looks like a rise of 4 and a run of 2. So that slope is rise of 4, run of 2. Sorry, f prime 4.5, that's right there. That's going to be 9 times 2, which is 18. Really, I can stop number crunching now. I mean, I can take this all the way down to like, this thing is equal to 18 plus 2 is 20. But what I really care about is the fact that that's positive. So, I mean, as soon as I knew that this number, this slope was positive, that was enough for me to answer this question. I probably didn't even really need to do the full calculation. Okay, but I would say that we are concave up at x equals negative 1.5 because, now I want you to notice how specific I'm being here. I'm not just saying g double prime of x. I'm saying g double prime at that point, right? So g double prime of negative 1.5 is positive. Okay, so I did the math to show that here. Again, really all I cared about here, because all these other numbers were positive, is as long as this slope was positive, that really would be enough for me to answer my question. Okay, and I could have told that just from looking at this picture. So really the hard part of problems like this should be these, right? Being able to write these equations. Once you have those equations, you can use them the same way we've always used them. Okay, like if you know you're talking about concavity, then you know you're using a second derivative. If I'm asking you about a first derivative, then you know you're looking at the graph and things like that. Okay, so getting this set up is probably the most important step. Okay, that should do it for today. We're going to practice with these a lot more, so don't stress about it, but this is really just a throwback to stuff we've done before. We're just putting new names on things. So good luck, and I'm sure I'll be talking to you about this.